Today's our lectures is about water flow under natural conditions. Okay, so this slide is about the spatial variability and transport. So here we can look at table 4.1. Table 4.1, you can get the value of mean and these coefficients of variation of various properties measured by Nielsen et al. In 1973 at the 150 hectare field site. So the 150 hectare field site is a large area, and in that large area they pick 20 sites. Okay, then 20 sites out of 150 hectare area. So they try to measure the infiltration rate, which is given by I. They also measure the saturated hydraulic conductivity, Ks, the saturated water content, bulk density, okay, and the water content at a particular metric section, and the diffusivity also being measured. So you can see the unit of each property that they measure, and you can see the mean value. The mean value is basically you just take the value of over the 20 sites, and then you average out by 20. Sorry, you divide it by 20, so you get an average value. So you can see that the average value doesn't tell you much, but if you look at these coefficients of variation, you could see that infiltration rate over 20 sites, you can have coefficients of variations of 94%, whereas saturated hydraulic conductivity is even larger. You have 120% variations, and if you look at diffusivity, it can go up to 258% variation. So sometimes it's very hard for us to say that at that particular area or land we have a value. Let's say infiltration rate is 14.6, because if we measure it out for over 20 sites of a location, we do get a spatial variability. Okay, spatial variability. So you can have a huge variations of infiltration rate. Is about 94% of coefficients of variation. And if you look at the diffusivity, is even larger, 258%. So spatial variability is always there. So the more location we collect for the parameter, the more representative will be the value that we measure for the site. For example, this case, infiltration rate is 14.6 centimeter per day. So this is the average value over 20 sites. Similarly, for saturated hydraulic conductivity, we have around 20.6 centimeter per day. So this is an average of over 20 sites. So the more sites we have, the more representative will be the mean value. And keep in mind that spatial variability is always there. And if you look at this, the spatial variability is over 100, is almost 120%. Okay, of the coefficients of variation. Field water balance. The general equation describing water balance is given by this: P plus I minus R minus ET equals to D plus changes of W. So P is basically the precipitation, include dew and frost, and I is applied irrigation water. So P is basically input, I is also an input. So I is irrigation water, P is precipitation, means rainfall. Okay. So and we have minus R. R is surface runoff, because it's negative because it's outflow. Okay, outflow from the storage. That's why you have a minus R here. And then minus ET. ET is evapotranspiration, the combined loss of water to the atmosphere from evaporation and plant water uptake or transpiration. So you have negative ET because it's a loss. Okay, just like runoff. Okay, and then equals to D. The D here looks positive, but if you move to the left side, then it becomes negative. So why it is negative? Because it's a drainage or deep percolation. Okay, drainage or deep percolation. So it's something like an outflow. Okay, all right. So that's why if you move here, it becomes negative. So you have three negative: negative R, negative ET, and negative D. But that is the reason why they moved the D here, and then we will look at it later on. And then plus changes of W. The W, of course, you can basically guess. Changes of W basically is a increase of water storage in the soil profile. So if it's positive, then it's an increase of water storage in soil profile. If it is negative, then it's a decrease in water storage in the soil profile. So you have a P plus I minus R minus ET is actually the net additions of water to the soil profile over a time period. So basically, it's how much water that's actually adding to the subsurface, to the what I call unsaturated zone. Okay, so then this P, I, R, E, T are positive in value, and D and changes of storage can be positive or negative, right? So if you have a D that supposedly is if you move it here, supposedly is negative, so the value has to be, the value itself is positive. The value itself is positive. So if this value become negative, then basically means that the water is flowing upwards. So if it's positive D, the water is flowing downward. So because D is basically referring to drainage or percolation or deep percolation. So itself, if it's positive D, you move here, become negative. So it's supposed to represent drainage or deep percolation. But if this value you move here become negative, and then the value, the D itself is negative. So if it's minus D and then the D is negative, then it becomes positive. So if when that case happen, the D is the negative D is showing that it's flowing upward. That's what it means. Okay, so I hope I did not confuse you on that. Okay, so water flow and water budget is important for various reasons. For example, if for hydrologists would want to know the fractions of precipitation result in direct runoff. So direct runoff means the water flowing on top of the soil, and a deep percolation to groundwater means the water that seep deep into the from the unsaturated soil into the saturated soil. Okay. And then for meteorologists, they want to know that they want to estimate the evapotranspiration since it has significant influence on the energy budget of the earth. As you know that when the water dry, the water carry a certain amount of what I call energy with it. So the surface that lost the water, the surface become cooler, and of course the vapor that vaporized from the surface, it carry the heat to the atmosphere. All right. And for plant scientists and agronomists, they want to know the evaporation losses by crops, because water is important for crops, and with root zone profile storage changes to determine optimum moisture condition for plant roots. So when the water losses from the surface or losses due to crop uptake, then the soil becomes drier. As a result of drying soil, the plant may not be able to continue to survive because water is needed for various what I call metabolic processes in the plant. Okay, now let us look at an example. So this is example 4.1. Let's say you have a land, a 9 by 9 meter square level field plot. Okay, a plot of land is divided into 9 3 by 3 meter square subplots. So you have 81 meter square, and then you break it down into 9 subplot. So each plot has a 9 meter square. So you have 9 of 9 meter square subplot. So each of which is plot of, which means 9 meter square for one side, and the other neighbor is also 9 meter square. But this neighboring plot does not connect with one another, so they are separated. Means water are not free to flow from one plot to another. So you have a 9 plot of 9 meter square area, okay, for each of them, and they are blocked off and they are separated from each other. So all plots are ponded with water until infiltration is constant. So the 9 values of infiltration rate, means this 9 meter square land. Okay, the area for each plot, for each subplot. Okay, so we are going to have a different infiltration rate. So the 9 value of infiltration rate measure are 0.5 centimeter per hour, 2.0 centimeter per hour, 7.0 centimeter per hour. So we have the lowest one is 0.5 until the highest one is 31 centimeter per hour. So if the entire field plot had been plotted, okay, what would the steady infiltration rate have been? So if the entire field plot had been pondered, what would be the steady infiltration rate have been? So here we can calculate the mean. So we can take all this value, okay, all this value, you add it up, you divide it by 9 of this value, so you get the mean value. So the mean value is 9 centimeter per hour. So that's the answer, all right, for this question. So what fractions of infiltration water would have gone into subplot area having a rate of 31 centimeter per hour? So this one, 31 centimeter per hour, the rate of infiltration for that particular plot. So this plot represents how many percentage of the entire, the other 8 plot. So how much does it take up? So we want to do that. So let's say we take we know the centimeter per hour. We can convert it into meter, all right, and then we multiply with the area. So we get this is the amount of water that infiltrate into the soil. Now this is a mean value. All right, this is the mean value. Okay, so now we can calculate for we can convert this 31 centimeter per hour rate of infiltration into a meter cube per hour also. So what we do here, take 31 centimeter per hour, multiply by the area, okay, of that subplot. So we can convert this 31 centimeter to meter. We have this value, and then multiply by 9 meters square, we get 2.79 meter cube per hour. All right, so here we have 9 meters square because this is a subplot has 9 meters square, and here we multiply by 81 meters square because the total area is 81 meters square. All right, and the total area is 81 meters square. We have 7.29 meters square per hour, but for this particular plot, okay, subplot, we have 31 centimeter per hour. So we get 2.79 meters square per hour. So 2.79 meters square per hour divided by 7.29 meters square per hour, multiply by 100, and we get about 38%, okay, roughly 38.27%. So this 31 centimeter per hour infiltration rate is actually representing 38% of the total infiltration of the entire plot. So this small plot of land that is only 3 by 3 meter square, that's a huge representation of the entire plot. Okay, yeah. So now at the final question, what would happen if the entire field plot were irrigated by a sprinkler system at 1 centimeter per hour? So if the subplot having 0.5, okay, so if you look at this, if the entire plot, so all plot 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 9 plot, each of them have water of 1 centimeter per hour. So what will happen? So you see, here we have 2, 7, 6.5, 5, 13, 31, 12, and 4. So all of these values are greater than 1, right? So only the first one is less than 1. So obviously, if you give 1 centimeter per hour to the first plot, this first plot will be overflowed with water because the amount of water that can enter into the soil is only 0.5. Right? So we have an extra 0.5 that is bonded on the top. So the subplot having 0.5 centimeter per hour, so means this plot would be ponded and sand run off to its neighboring plot. So this plot will be ponded with water, and the water here ponded will flow to the neighboring plot. Okay, that's what happened, right? Thank you. Okay, so this slide shows the analysis of field water content and metric potential profile. So you can look at these two graphs here. The y-axis is a soil depth. So 0 is the soil surface. So if we move 1 meter downward into the soil, we have -1 meter, up all the way to 8 meters. So they measure the what I call here in this case is volumetric water content or soil moisture content up to the depth of 8 meter into the soil, from the surface to the depth of 8 meter. And then they found that the water, the volumetric water content changes with the depth. And then this is, of course, A is a young sand from Mount Gambier Forest, and this figure B is a Kalangadu sand at Penola Forest. All right, so you can see that there's a lot of changes on the surface, but as we go deeper into the soil, there's not much changes. Obviously, what I mean by changes is that a lot of changes here means at different time of the year. For example, from April, July, September, and November, there changes from month to month. But if you go deeper, the soil moisture content stay relatively constant. Okay, relatively constant. All right. So same thing also happen in figure B. You have more changes at the surface, but as you go deeper, the soil moisture content at different months would remain relatively constant. Right. So the fluctuation in water flux and water storage occur simultaneously near the surface, but changes occurring at greater depth are frequently very small. Okay, if you go deeper, the changes at that deeper depth very small, and the steady state model provides a reasonable approximation to real system. So if you have a steady state model, so you can more or less do some approximation of the soil moisture content at depths. So that's what it means. Steady state model provide reasonable approximation to the real system. All right, and then we have a P, which is precipitation, and I, irrigation, can be accurately measured at the field. Because you can use a rain gauge to measure precipitation. We can know how much water we supply to the field from irrigation, and runoff can be monitored at the downstream end of the field. So if you have water flowing out from the field, so you can take that as a runoff, and the evapotranspiration is straightforward to estimate. But the deep population is by far the most difficult to measure or calculate. And the rainfall and evaporation are very pronounced near the soil surface, but diminish significantly at greater depth. So what it means that if you have a rain coming in, so the rain will fill up, so the water content will rise. But then when it comes to dry season, the water content will drop. Okay, so water content drop because water flowing down. That's first, and secondly is the evaporation from the surface because of high temperature. Okay, so rainfall and evaporation has a huge impact on the surface. So you can see that at different place you have the same trend of observation. Okay, now let's look at infiltration. Infiltration means water entering the soil. All right. So empirical approach to the development of field infiltration equation. Okay. So it means we observe that there's a certain pattern that water entering the soil. So we do this empirical observation, means field observation, okay, or laboratory observation. So means it's what I call this is human observation. Okay, empirical approach to the development of field infiltration equation consists of first finding the mathematical functions whose shape as a functions of time matches the observed feature of the infiltration rate, and then attempting a physical explanation of the process. So means we do some kind of curve fitting, okay, to the observation. That's what it means. But mechanistic basically means something more on fundamental, the governing equation or the fundamental force behind, for example gravity, things like that. Okay, so that's called a mechanistic approach. Mechanistic approach consists of solving water flow equation to derive an expression for the infiltration rate. Okay, so you can assume that they are referring to Richard's equation as in this case. So time dependent is that metric potential gradient has decreasing influence as a vacuum fronts move farther from the surface during infiltration. So as a water infiltration front moving deeper into the soil, the metric potential gradient has less influence, but gravity flow is more important. Okay, so here is the Horton equation. So Horton equation represent the infiltration rate. So we can see I equals to IF. So we have a IF, which is the final constant infiltration rate at large time, and then you have a I naught. Okay, I naught is initial infiltration rate at t equals to 0. So infiltration rate, you can refer it as meter cube over second, or you might want to call it as a meter per second. All right, but normally we call it meter cube per second. All right, so we have a meter cube per second, meter cube per second, meter cube per second for all of them. All right, and beta is a soil parameter describe decreased rate of infiltration, and of course t is the time. Right, so this equation represent the meter cube per second, so the infiltration rate, and you can rewrite it as d changes of volume, okay, divided by the changes of time, and then you do the integration for this equation, and end up you get the volume, how much volume that entering the soil at different time. So this is how you can estimate the volume into the soil. Okay, here is another equation called green M infiltration model, and the figure here 4.4a is show you the actual soil, the water content distribution in the soil as a water infiltrate into the soil. So A is a soil water content profile during infiltration process. So this is the actual observation from experiment. But the B1 is a simplistic, okay, model that given by green M, okay, green M model. All right. So green M infiltration model is an approximate mechanistic model of infiltration process. So in infiltration event, soil surface is at constant metric potential head. So metric basically means a metric suction. Here is H naught with the water content theta naught. Okay, that's what I mean. Water enter soil sharply defined wetting front that move downward with time. So you see that the water entering into the soil, but it happens so sharply. You see, the actual one is not so sharp. It has a wetting front that is not exactly sharp. But this green M model, it gives you the water front, but it's very sharp. Okay. So it has discontinued change in water content at the wetting front. So the wetting front, suddenly we have water, full of water, suddenly no water at all, or little water. Okay, so that's what happened. The discontinuity happened here with a green M model. So assumption is soil at wetted region. So soil at wetted region here has constant property. So we have a saturated hydraulic conductivity at K naught, diffusivity naught, theta at saturation. Okay, theta means soil moisture content at saturation, and metric suction also at saturation level. Right, the metric potential head at the moving front is constant and equals to HF. So here you have a constant HF. I mean soil moisture, soil suction value is always constant. Right. Okay, now let us look at the example 4.2. So example 4.2 used the green M model to calculate the infiltration rate into horizontal soil column. So the soil column is horizontal, initially at a uniform water content theta I. So initially the water content in the soil is theta I, that has a water content theta naught, okay, greater than theta I. So the water infiltrate into the soil column that is horizontal. So the water that enter is at theta naught. Okay, and associated metric potential H naught maintained at the entry surface for all. So when time is greater than 0, so the water that entering into the soil is theta naught, and the corresponding metric potential is H naught. Okay, so right. So infiltration into horizontal soil. So at time t with uniform wet region of thickness L, all right. So thickness L, all right. The infiltration rate as I, okay. So the rate of water entering is I, and here we're using Darcy's law. So I equals to ZW. So the water flux equals to negative K naught. Okay. And then this is the hydraulic head. Hydraulic head here, you can assume that the entry point is H naught. The end of the soil column is HF. So we have a distance from Z1 to Z2. So their difference is L. So we can take HF minus H naught equal divided by z2 minus z1. Okay, here we have a negative. All right, so we can rearrange this equation. You will get h naught minus hf divided by z2 minus z1. Only the top that changed, so the negative value you bring in here, so you change the position, and now we can rewrite this whole thing as a change of head divided by L. So z2 minus z1 is L, and h1 h0 minus hf is the changes of head. Okay, so the changes of head equals to h0 minus hf, and they are they are greater than 0. So the infiltration rate is I, as shown here, equals to the derivative of the difference of water content. Okay, the difference of water content theta naught at the entry point, and the what I call the uniform water content, the initially uniform water content in the soil is theta I. So theta naught at the entry greater minus the theta initial in the soil column, and then in the bracket you multiply with the length of the tube. Okay, length of the soil column, and this is the derivative, and then of course the theta naught minus theta I can be written as the changes of water content, and of course the L you maintain. So you take the derivative, you take this as a constant, and then now you only have a derivative of time on the length of the soil column length. Okay, so the theta naught minus theta I is greater than 0. Okay, now you can rewrite this infiltration rate I equals to changes of water content, the derivative of length with time. You can write it here, and then this I itself also equals to the saturated hydraulic conductivity, and multiply with the spatial derivative, and then you can also write it here. Now you can rearrange this equation and take the integration from time 0 to time t, from initial time to final time, and then you integrate from 0 to the length of L. Okay, so you have L squared divided by 2 equals to k naught multiplied by the difference of H over the difference of water content multiplied by time. So the k naught multiplied by the difference of head divided by the changes of moisture content is given by this d naught. Okay, so now you have this L. Now you can rewrite this equation as L equals to the square root on 2d naught multiply with time. All right, so if you want to find the cumulative inflation, that will be I. So in this case, it's very clear to you that I has a unit of meter, because you see the changes of water content is actually meter cube or meter cube, and the L has a unit of m, because it's a length, right? So I obviously has a unit of meter length. All right, so the L now can be written as this can be replaced by this equation. So you have a new equation for cumulative infiltration, but this one has a unit of meter. Right, so we can rewrite it back for infiltration rate I, which is what we call we have this in the previous slide. Yeah, this one. All right, so the derivative of cumulative infiltration with time. Okay, so the cumulative infiltration, the time derivative on the cumulative infiltration, we'll get the infiltration rate. So obviously this unit will be meter over second. Then if we put in the cumulative infiltration here, and then in the end, at the end of the derivation, you have I equals to changes of water content, and then you take the square root on d naught divided by 2 time. All right, so you can see that the infiltration rate I is actually proportional to time to the power -1 over 2. Okay, so time to the power -1 over 2. Okay. Alright, so here's example 4.3. So example 4.3 repeat example 4.2, but now we do it for vertical infiltration. So I'm not going to discuss about derivation, and the derivation is already given here. So if you're interested, you can look more into this. Alright, so apart from green M, there is also Phillips infiltration model. So Phillips infiltration model is another types of water infiltration model. So Phillips addresses horizontal infiltration. So it means there's no gravity because the flow is horizontal. Using Richard equation, okay, so they solve. So Richard actually solved Richard equation, which is different from green M, because green M does not solve Richard equations, and Richard equation is more more representative of the flow. Okay, so using Richard equation, infiltration rate I equals to 1 over 2 s multiplied by time to the power of -1 over 2. So where s is function is known as a sorptivity. It's a function of boundary theta naught and the initial water content theta I. So s increases as theta naught increases. So if you have incoming water at a higher water content, so the s will be increases. So since theta naught at inflow boundary is held constant and theta I is also constant, hence s is constant over time. Alright. So cumulative horizontal infiltration. So I equals to the derivative of derivative of I with respect to time. So you can do that, then you get I equals to s multiplied by t to the power 1 over 2. So s may be determined from slope. So slope of I versus t square in horizontal infiltration experiment. So you can plot the graph showing the cumulative horizontal infiltration, and then as a y-axis, then the x-axis you have a square root of time, and then you can get the slope for different line. So the line with higher slope, you get a larger theta I, sorry, theta naught. Okay, so this is how you can actually determine the s value. Okay. Okay, so similar to green M solution, this Phillips semi-analytical equation can also be used to determine this vertical infiltration. Okay, so here's an explanation of the vertical infiltration into the soil. So if you are interested, you can read more into this. So the graph here show you the infiltration rate with time. So this is the kind of information you can get with the Phillips water infiltration equation. So as you know, water infiltrate into the soil, and also depending on the soil type. So let's say, for example, it's a sandy loam, and the water can infiltrate easier compared to silt soil type. Okay. Okay. This figure 4.6 shows the measured and predicted soil water profile for air dry Hesperia soil allowed to wet at theta naught equals 0.385. So here's the dot is the experimental data, and the solid line is the simulation result. So at different time, at a longer time of simulation, or at the longer time of water infiltration, the water will go deeper into the soil. So you can see that there is a good match between the experimental data and also the simulation result. So there's also other infiltration models, for example, Habercam models, and also Sandrubo models. Okay, now let us look at field versus laboratory infiltration. So field basically means we do the infiltration test at the field site, and laboratory infiltration means we conduct the laboratory experimentation. So the difference is that in the field experiment, we test it on the real soil. The soil is undisturbed. Okay, that is a natural soil in the field. But in the laboratory, we might need to dig the soil and collect the soil and bring it back to the laboratory. So normally the laboratory test is more ideal. It's not a natural process because we might have altered the structure of the soil as we dig the soil and bring it back into the laboratory. So some of the differences that worth noticing is that the models that we use to model the field and the laboratory is same model, but it neglects certain important factors that only exist for the field soil. So these factors, for example, is the possible entrapment of air in the soil profile during infiltration, but this is true for both field and laboratory. So, but laboratory, we can try to avoid the entrapment of air by creating a certain condition where air entrapment can be avoided. But in the field, it's almost impossible to neglect the effects of air entrapment because of soil homogeneity. Okay, so these are the possible differences. And the development of surface crust that decrease the hydraulic conductivity. So the soil surface subjected to hot weather and cold weather at the same time. So there's the surface going through hot and cold over the years, and over the years also there are many heavy machinery, including human footsteps that pass through the area. So this might create a surface crust at the top of the soil, and this can actually decrease the hydraulic conductivity. So that is true particularly for field soil rather than laboratory. For laboratory, for example, if we dig the soil, we bring it back to the laboratory, and then this surface crust might have been destroyed. So we can't get the same condition as the field soil, right? And then of course there is a microbial growth. So at the field soil, we might have this microbial growth effects on the laboratory, on the infiltration process. Rather in the laboratory, we might accidentally remove that effect from taking into account. Vertical movement of earthworm that may lead to increased hydraulic conductivity and infiltration rate with time, because the earthworm, their purpose is to make holes in the soil. So when they are moving or moving through the soil, they create this porous path. Okay, so they create this kind of path where water flow become easier. All right, and also at the same time they discard certain liquid into the soil, which make the soil sticky in some place and more porous at the other place. Right, so these are the differences. So another thing that worth mentioning is that the Horton equation predicts infiltration rate decreases to a constant value in 2 to 3 days, 2 to 3 hours when used in a few calibrated parameters. Whereas for Phillips equation may continue to decrease for days. Okay, so these are the primary difference between Horton equations and Phillips equation. And field soil profile are seldom uniform. So that means that they are not homogeneous. Okay, with that, nor is the water content distribution uniform at the initiation of infiltration. So what it tells you is that in the soil in the field, they are basically in a mixture of different kind of particle size. Okay, you might get clay, silt, sand distributed all over the place. So they are seldom homogeneous. Okay, and they varies with depth. Okay, not only with depth but also spatially, right? I mean vertical surface in terms of surface, spatially, right? And the water content in the soil is also different. Sometimes in a deeper soil, you get more water. At the surface of the soil, you get a drier soil. So they don't have what I call uniform distributions of water content throughout the soil. And the surface sealing caused by sediment deposit from muddy water irrigation. For example, if you look at flooding, for example, right? So the flooding carry all the debris, all the kinds of particles, and then after the flood disappear, you can see there's always a layers of soft materials left on top. So mostly those soft materials are very fine particle. So this fine particle could actually cause sealing. So this is what we call surface sealing caused by sediment deposit from muddy water irrigation. So this kind of process is normally happening after flooding, things like that, or even a river that has a very low flow rate. Okay. Another influence is water table when near the surface, right? So water table can rise and fall. So at certain period of time, the water table can actually rise to the surface of the soil, and of course, because of that, it alters the infiltration process. Right. So when the water table is very near to the surface, it changes the water infiltration into the soil. Right. Not yet a viable mechanistic infiltration model that includes the effects of earthworm and other burrowing organisms. So earthworm is, as I mentioned to you, it can create a tortuous path in the soil. Other burrowing organisms, for example, these ants, these are termite. Okay, so they are making holes in the underground. For example, mouse. Okay, so they are burrowing organisms, so they can actually make holes. Beetles, for example, yes, ants, I already mentioned that. So there are various kinds of organisms that can actually do that kind of boring. So when they're boring, they create a space where it's very porous to water flow. All right. Right, now let's look at infiltration when rainfall is limiting. Okay, if rainfall rate is so intense, so means a lot of rainfall, ponding begins immediately. So means takungan air berlaku secara serta-merta. So for example, in this condition we call it positive pressure head because air takung di atas permukaan tanah. Alright. So if rainfall never exceed final gravity dominated infiltration rate of the soil, there will never be any runoff. So means if the supply of rain is fully absorbed by the soil, fully infiltrate into the soil, there will not be any water that left behind on top of the soil to be taken as runoff. So all the water hit the soil will be absorbed into the soil when the rainfall rate never exceed final gravity dominated infiltration rate of soil. Right. So when rainfall rate is lesser than initial infiltration capacity of soil, but greater than final steady state gravity dominated rate, soil will absorb incoming rainfall until metric potential gradient near the surface diminish to a point where water cannot be taken up as fast, which now is dominated by gravity. So hence, surface soil saturate and ponding develops. So as you know that water infiltrate into the soil is governed by two mechanisms. One mechanism is the metric gradient, right? And the other mechanism is the gravity dominated mechanism. Okay, so when rainfall hit the soil, this metric potential gradient will mechanism will absorb water into the soil. At the same time, that is also gravity. As the water infiltrate into the soil, the metric potential effect become lessened. Now it is only governed by gravity effect. So at this stage, the infiltration rate may not be so high as the initial state of water infiltration. Right. So when rainfall rate is lesser than initial infiltration capacity of soil, but greater than final steady state gravity dominated rate, so initially all the water will enter because the water will be absorbed by the into the soil due to metric potential as well as the gravity effect. But as the metric potential effect has been weathered out, once the soil is fully saturated, only gravity effect is happening. But the rainfall rate is lesser than initial capacity of the soil, but greater than final steady state gravity. As a result, we have surface soil saturate and then ponding start to develop. Okay, that's what it means. So here you can see that this is a figure 4.7 comparison of constant flux infiltration. So you have a solid line, okay, at infiltration rate greater than Ks, with means it's greater than gravity, okay, with maximum potential infiltration by continuous ponding, and then here we have a dash line. So dash line is continuous ponding. This solid line is a infiltration rate. So solid line here, if you look for the numbers on the figure, refers to value of I divided by Ks. So the infiltration rate here, you have infiltration rate here I divided by Ks, so you have 4.5. I divided by Ks here, you have 3.0. So I divided by Ks here, you have 2.25. So here you have a greater infiltration rate, lesser infiltration rate, and the lowest infiltration rate. So this infiltration rate basically means that it is not fully saturated. There's no ponding happening. So we have direct incoming water from rainfall, for example, or irrigation, for example. So, but if you compare to the dash line is referring to this ponding condition. But if you look at here, if you look at ponding, initially it is very high infiltration rate because there are metric potential gradient as well as gravity mechanisms happening, right? But as the water entering into the soil, we are left with the gravity dominated mechanisms. Even though it is not ponding, you can see that the water will enter into the soil at a high infiltration rate, but it will slowly lower down to the stage where it is governed by gravity effect. So the same thing happened at different infiltration, we call that different rainfall, for example, okay, different rainfall, 4.5, 3.0, and 2.25, which is given by I over Ks. So the I might be very high for 4.5, the I is very low for 2.25. So that's what the figure means. So ponded surface condition, dash curve. So this dash curve, so it means water ponding on top of the soil. The constant rainfall input, this is solid line, so this is due to rainfall. So here you have higher rainfall, medium rainfall, and lower rainfall. But eventually you end up with the same infiltration rate, which is dominated by gravity. Okay. So factor not considered by model based on Richard equation, for example, this surface ceiling will have a significant influence on the time to ponding. Okay, so here we look at the infiltration into a layer soil profile. Alright, so here we have figure 4.8. We have infiltration and movement of water in a layer soil with the finer texture soil on top. So here we have a fine texture soil. A, which is the yellow clay over quartz sand. Alright, yellow clay over here is a quartz sand, and then B is a yellow clay over oak lay sand. So yellow clay at the top, and then you have a oak lay sand. Right. So figure 4.8 shows the wetting front stop temporarily at the interface. So water adding at the top. So but then it stopped temporarily at the interface until pressure rises enough to fill the large pore of the sand at one location. So the water will keep on rise, saturate up to a point that it can enter the large pore of the sand at one location. So after which all of the flow from above was carried into a single channel. So all the flow from above was carried into a single channel of a highly conducting wetted sand. So the water then just flow down. So this is kind of what I call preferential flow is actually happening, right? So due to coarse sand in the lower region, so it's a coarse sand at the lower region has negligible conductivity at the metric potential of the wetting front. So the wetting front, the suction of the wetting front is very high, but the suction will reduces as the water content increase up to a point that it is significantly low metric suction. As the water build up, then the water just enter into the sand at the large pore, right? So water cannot enter the coarse texture zone until pressure has built up sufficiently to wet the larger pore. So the pressure build up, so it means the metric suction reduces from negative to zero, possibly to zero, and then create a positive pressure. Then the water will start to entering the soil, okay, entering the sand. The quartz sand, right? So this is what happening. So figure 4.8b, the sand temporarily slow down. The sand temporarily slow down the infiltration, the infiltrating front from the overlying yellow light. So like yellow light at the top. So water enter, but it is slowed down by the layer of yellow clay, but allow water to enter over the entire interface boundary and no finger form. So So the water is allowed to infiltrate into the sand area, but very slow. This is slowed down by the yellow clay. So we can see that the infiltration also happening, but it is slowed down by the yellow clay. So here is the measurements of infiltration. So the infiltration measurement method that we can use is one of them is a ring infiltrometer. So it measures the infiltration rate of water into the soil. It may be a single ring or with additional larger buffer ring surrounding the inner ring. So say you have one ring, you can have another ring surrounding the inner ring. So we have double ring, for example. So Marret reservoir, so this is a Marret reservoir, is used to keep the ponded height constant. So the ponded height, here this is a ponded height. We can keep this ponded height constant by using the Marret reservoir, and also to measure the water volume entering the soil. So this is the volume, and then you can have a measurement of liters of water. So as the water level drop, you will know that how much water actually entering here. And this tube is to keep the water level at constant. Alright, and it can also be used to estimate the saturated hydraulic conductivity. Okay, so if you look at this diagram again, you can see that the ring is a small portions of the ring actually entering into the soil, and then you can also have a tensiometer inserted into the soil, and then water will actually entering into the soil, and then of course you will have these formations of wetting front within the soil. All right. So let's try to understand how a Marret bottle actually works. So the Marret bottle works like this. You have a tube where air is allowed to enter, and then inside the what I call the container, you have the water raised to a certain height, and then you have another tube inserted into the container. But this tube is filled with water, and then to the pipe, and then to another location. So what is happening here is that as the water flow out from this tube, the water from the air, the air is allowed to enter into the air tube, which fill out this empty space, right? So you can see here, you have an air bubble coming in. So when the air bubble coming in, the point where the air bubble coming in is the point where you are actually at the atmospheric pressure. So here is atmospheric pressure, and here is also atmospheric pressure. So you have the same atmospheric pressure. So when the water is lost here, now the air from the atmosphere will enter into the space and fill up the empty space, fill up we call increase the air space here, and then of course the water will be coming out from the other tube. Okay. So if we re-examine this diagram again, the Marret tube water, the Marret bottles, so you can check the energy total potential at a different point. For example, you have a point near the reference, and then the point above where the air location is, right? So you can look at here the water level point, where if you check the gravitational potential, it is actually positive 20, because gravitational potential is based on elevation, right? So the gravitational potential here, elevation, is plus 20. But if you look at the pressure is, if you look at here, is 20 centimeters above the reference point, but the atmospheric pressure is here, right? So you rise above the atmospheric pressure here, so you have a negative 20 centimeters, right? So if you calculate the total energy, total potential is 0, right? So if you look at the reference point, okay, where the air bubble actually enter, so the gravitational potential is elevation is 0, so then the pressure is 0, because this is a reference point. So as a result, total potential is also 0. So you have a 0 and 0 here at both points. Okay. This is a diagram shows a tension dish infiltrometer. All right. So you have a reservoir, you have a bubble tower, you have the contact sand at the bottom, and then the contact sand at the bottom has a radius r, and then of course you will have a pressure head where the water actually are being pressurized from the top, and then we have of course the influx of water into the soil. Okay, so true saturation is rare in the field because of air entrapment. So means the soil cannot be truly fully saturated, because there is always some air is trapped somewhere in the soil. All right, so maximum hydraulic conductivity is attained naturally is often less than true saturated value. Okay, so the maximum hydraulic conductivity is attained naturally is less than the true saturated value because of the air entrapment thing. Okay, so this is known as near saturated or quasi-saturated hydraulic conductivity. Okay, so we can never achieve the real hydraulic conductivity. So the measured value of hydraulic conductivity in the field is somehow less than the true saturated hydraulic conductivity value. So the tension disk in filtrometer, to determine tension disk in filtrometer means this kind of measurement unit. Okay, tension disk in filtrometer to determine the contributions of micropore to infiltration rate and conductivity at saturation. So you can use this tension disk to investigate certain pore that contribute to infiltration and also conductivity at saturation. Right, chamber with a permeable porous plate. Okay, so a permeable porous plate at the bottom, or cloth at the bottom that support a modal suction. Okay, which is maintained by a Marriott bottle feeding the supply reservoir. So the Marriott bottle here. So this Marriott bottle we can use to manage the pressure that applied to the porous plate. Okay. So water to infiltrate under a specific suction sufficient to prevent entry into macropores that reach the surface. So what does it mean? Water to infiltrate under a specified suction sufficient to prevent entry into macropores that reach the surface. So it means at different suction, different macropores are being investigated. Okay. So suction can be varied to describe macropores in various tension range. So okay, here is a figure 4.11, which shows the hydraulic conductivity value of 5 Iowa field soil measured with the tensile disk infiltrometer at various values of infiltrometer tension in millimeter. So it means infiltrometer tension means at different suction value. Alright, so you can see that the hydraulic conductivity for different soil, but ultimately if you increase the suction at very high suction, so you are getting a lower hydraulic conductivity. So the hydraulic conductivity generally drop with increasing infiltrometer tension. All right. So this slide we look at the infiltrometer diagram. This is figure 1. This is a measurement unit from Decagon, and now it's called meter group. All right. So in this diagram, you can see there is a water reservoir at the bottom. So you also have a bubble chamber at the top. So they are separated by the chamber barrier. And then you have a suction control tube, which is graduated. Basically means it has a reading in a centimeter. And also you have this graduated measurement on the this what you call it, water reservoir bottom part. So you can see it can go up to 100 milliliter. All right, and then at the bottom you have a sinter steel disc. Sinter steel disc is the disc is actually perforated, so it is a porous disc. Okay, porous steel disc. So this porous steel disc put on top of the soil. All right, and then we will fill out this part, the bubble chamber. We will fill up with some water. Okay, as shown in this figure 2. So filling bubble chamber with some water. Right, and then you can open up the bottom of the sinter disc, and then you can pour in water. Okay, so remove bottom elastometer, and then pour in water into this water reservoir chamber. All right, and then what you do is that you can adjust the height of this suction control tube. So here you can see that they put it around 3 centimeter. So the suction is about 3 centimeter, right? So the air has a certain pressure, but in this case it's a negative 3 centimeter. Okay, so the air pressure in this chamber will be negative 3 centimeter. So the water suction that entering into the soil is based on negative 3 centimeter. So as shown in this case, so it's 3 centimeter suction rate. And then of course you need to measure the drop of volume in the water reservoir from one volume to another volume. At the same time, you also need to record the time. Preferential flow of water and solute. Preferential flow means the water prefer to flow at certain region of the soil. So it is due to macropore flow, funnel flow, and unstable flow. Okay, macropore flow. So it is flow through part of soil that contain structural void or other conduit with a large opening. So basically means you can imagine it as some kind of tube that opening for the water to flow from the top to the bottom, something like that. Okay, it could be caused by soil shrinking by drying. So maybe the soil that's wet is a bit bulky. So when it's dry, you open up space, cause some crack. So that becomes a macropore for water to flow through and become easy. Chemical weathering, something like the soil that has some kind of mineral, for example, I don't know, this kind of Chp4. All right, so they can be easily dissolved in the water. Maybe the water has some high pH value due to acid rain, so it dissolves the chemicals that open up the space where it creates macropores for water to easily flow through. There is also possibly cycles of freezing and thawing. Freezing is cold, thawing is hot, warm. So cold and warm over the period of time can create the kind of macropores where water can be easily flow through. Biological activity, for example, your soil has lots of organic materials. So these organic materials become the food or source of resources for biological activity to take place. As a result of that, it changed the macropore, possibly create more space, or I think in most cases, it creates stickiness in the soil that make it hard for water to actually getting through the soil. And tillage destroy macropores. For example, if you look at this heavy machinery that's doing the tillage activity, it could destroy by compacting the soil, causing the macropores are being destroyed as a result of the tillage activity. Macropores flow in a dominant in a fractured rock due to rock medium has extremely low permeability surrounding fracture that has extremely high permeability. So it means that the rock that is fractured, the water can easily flow through the fracture space between the rocks, so that create easy flow for the water. And the theory of flow based on homogeneous media, for example, the Richard equation, so did not adequately describe field observation, because most of the soil in the field observation have at least some macropores in them. Okay, so here is a study for the preferential flow, right? So there are 40, this is a case study for 14 major agricultural soil in Switzerland. Irrigation by sprinkling 4 centimeters of water containing dye. So they sprinkle the soil with 4 centimeters of water that has dye, which is brilliant blue FCF food grade, onto 2 by 2 meter square plots. Okay, each soil has 2 plots. Okay, one is a natural state, so one is without any altering, they just open to the sprinkling, and a second plot covered to prevent water entry for 2 months before water sprinkling. Okay, so after 1 day of irrigation, the plot was excavated and a stain pattern was examined on a vertical 1 by 1 meter square of soil profile. So here's the result. You can see that the dye accumulate mostly at the top, and it reduces as we go deeper. This is the same case for most of the site of the study, but you can see that but it is slightly different from place to place. What you can see is that water bypass the soil matrix in most cases, so it means the flow is not uniform in most cases. Structure soil aggregate more prone to bypass flow. Okay, so the flow does not happen uniformly throughout the soil. It flow more on certain area than the other area. Okay, that's why you see that this is an indication of some kind of preferential flow. So structure soil more prone to bypass flow, and deep dye penetration. Okay, you can see that deep dye penetration actually happening. For example, this case, you have a deep dye penetration, but here not much of penetration actually happening. But if you look at the other three, you have a deep dye penetration, and the pulse splitting and you can see there's a pulse splitting. So you can see the pulse coming in and then drop and then rise again. So some kind of pulse splitting actually happening within the soil. And the figure 4.14 shows four-side flow channeling varied from moderate to extreme. Okay, so some kind of channeling flow is actually happening. So basically that means preferential flow is actually happening within the soil. So here is another figure 4.14, sorry, 4.15. But you can see that what is different here is that there are two soil, that one is wet and one is dry. Like previous slide, we mentioned that one is natural and one is being covered. So one is natural, so the wet one, the completely black bar is natural, and the white bar is being covered to prevent entry for water for more than for 2 months before water sprinkling. So you can see there's different here is that 4.14 shows the maximum observed depth of penetration of the dye in all plots for both wet and dry initial conditions. So the sprinkling of 4 centimeter water would penetrate 16 centimeter in the soil with a porosity of 0.25 meter cube over meter cube. What does it mean is that if they give the soil at different location, if they give the soil 4 centimeter of water, if the soil has a porosity of 0.25, which is the soil characteristic of the site, the water can only enter as deep as 16 centimeter. Okay, 16 centimeter. But here you can see that the dye actually penetrate up to 100 centimeter in a few locations, and then most of the cases is more than 16 centimeter. So since most soil have water penetration greater than 16 centimeter, there were significant preferential flow. Okay, so there is a certain path in the soil where the water can easily flow through than any other soil type. So there's something like this happening, which is happening in the soil. So based on their calculation, the water, if it's uniformly absorbed and infiltrate into the soil, it can only infiltrate 16 centimeter for 4 centimeter of water that provided to the soil. But in this case, they can go up to 100 centimeter. You see, in some cases, or at least you can get up to 40 centimeter. And then the wet and dry is also not much different, but in some cases they are lower because this dry soil, they are being covered up, okay, for 2 months without exposing to any rainfall. So you can see that there is some kind of preferential flow is actually happening in the soil. So you can say that the soil is non-homogeneous in general. The flow, some certain portions of the soil or the matrix of the soil, certain part of the matrix of the soil are more prone to flow than other metrics of the soil. Okay. All right. So here is an example of funnel flow. So let us look at figure 4.16. Figure 4.16 is showing the schematic illustration of funnel flow, showing discrete lenses of coarse or finer material, and then the surrounding permeable matrix. So we have a discrete lenses. So you have a lens that appear in the subsurface in the soil. All right. So water will move around both kinds of lens. What both kinds of lens means, the lens that referring to this coarse or fine lens. Okay. So it can be a coarse, it can be a fine lens. All right. And water will move around this kind of lens and causing water to channel into a narrow plume. So the water will, when it hit the lens, it will flow to the side. And then when it hit the lens again, it will flow to the side again. So sometimes it might gather. Then we have this kind of funnel flows actually happening. All right. So funnel flow, the coarse lenses acted as a barrier. So this coarse lens acting as a barrier, as a restriction when dry, channeling the water around them into smaller and smaller pathway. So the water will move on the side. Move around it. Okay, so they will move they will gather at one place. So over if this kind of patches this kind of lenses appear all over the soil. It might gather in one place, so it feels like a funnel. So it gather and forms like a funnel. So you have a funnel flow. So the conductivity of the surrounding matrix was high, and this pathway was still able to transport water without lateral spreading. So means the conductivity of the soil is still high enough that the water can move down without having to move to the side. Okay. So similar thing also happen for fine sand. So if this is very coarse sand compared to the surrounding soil, this what I call funnel flow could happen. If this is very fine sand as well, funnel will still happen. So it is a relative comparison with the length compared to the substrate of the majority of the soil. So it can be very fine, or it can be very coarse. So if that things happen, if you have something like this appear in the subsurface, you will have a funnel flow. Since because water cannot get through the lenses, it has to pass by the lenses, and then it will form some kind of funnel as it flow down the stream of flow down through the matrix of the soil. Alright, so this is an unstable flow. Unstable flow, it is associated with vertical flow from a fine texture layer into a coarse layer. So you might have a clay soil on top of a coarse sand. Okay, and another one is the vertical flow into a compressed air phase. So you might have a vertical flow, but at the bottom you have a soil that has a compressed air phase. Alright, so infiltration into water repellent soil. So you might flow from a soil that has less water, that has no water repellent, into a soil that has water repellent. For example, organic soil. So two-phase flow involving two fluids of contrasting density and velocity. Alright. The unstable flow is distinct from other forms of preferential flow in that it is fluid phenomena, whose extreme flow location is not a consequence of permeability variation in the porous media. So this kind of flow happen. It's not due to the difference of permeability, but actually it's due to the fluid phenomena, which is the natural behavior of a fluid that causes fluid to flow in such a way. Alright. So this figure 4.17 shows the development of a fluid instability during redistribution when the pressure distribution decreases towards the surface. So if you look at this soil, you can see that if we move from the wetting front, which has more water here than the water at the surface, so the water actually gathering at the bottom. So here the metric suction is not so high, but here the metric suction is very high, means a very negative value. Here is less negative value. But when we talk about potential, here has more potential than the potential over here, as I described here. So the darker shade indicates wetter soil. So here's darker, you have a wetter soil. Here it says that you have a higher metric potential. So you have a higher metric potential here. Alright, but here you have lower metric potential. Okay, lower metric potential. But what does it mean? Is that here is drier, so you can know that from a drier soil you have a very negative metric suction. So you have here less negative metric suction, right? So if it's completely saturated, then it is zero pressure. Okay, so what you can see from here, what you can assume from here is that here it has more water content, here you have a lower water content. So let's try to understand this. When the front advances ahead at one location, so let's say of all these initially at the same level, let's say one part of the front move down, so the front advances ahead of one location, so here advances ahead of one location, the pressure distribution above it shift upward. So the pressure distribution initially is the same from the wetting front to the surface, but suddenly here the water suddenly flow down. As a result, the pressure distribution will also shift down, right? So the pressure distribution shift downward, creating a lateral flow gradient from adjacent region towards the finger. So when the water at this part move down, it create the flow region, the lateral flow region from adjacent region. So adjacent region, this is adjacent region flow towards the finger. So this is the finger that has been shift down. So this is what happened when you have an unstable flow. Alright, so here's an example of water ponding on top of the soil. So water ponding causes instability and of course subsequently water distribution in the soil. So you can see the formations of finger in the soil. Alright, and you can see that the formations of fingers becoming more prominent, or the fingers grow bigger and bigger at a different time. Okay. Right, so this figure 4.19 shows the difference of sand and clay. You can see that in the sand, the water can infiltrate deeper into the soil depth at the same time compared with clay soil. So in the clay soil, water cannot penetrate deeper into the soil as sand. So for sand, it's easier to move in. But you can also say that in sand, the gravity is more prominent. It's more dominant than metric suction force. But in the clay soil, the metric suction force is more dominant. So you can say here is that if the metric force predominate, the wetting front tend to be more symmetrical. So it means the water move lateral and vertically is almost the same. Okay, because metric force is more dominant in the clay. In the sand, gravity is more important, more predominant. As a result, you have a more elongated flow deeper into the soil. The water flow deeper into the soil. So you have a shape of elongated flow of water. Okay, so this is a slide shows the redistribution of water in the soil profile. So redistribution refers to the continual downward movement of water through a soil profile after irrigation has ceased at the soil surface. So it means that initially you provide irrigation to the soil, but then after some time, at t equals to 0, you stop irrigation. This is an example. So you provide irrigation at the top of the soil, suddenly you stop irrigation. So what happened? The water initially has penetrated into the soil at t equals to 0, and then when you stop the water, the irrigation water, the water at the surface will continue to dry. Okay, so the water content of a vector profile decreases uniformly over space, but no abrupt drying of the surface layer. So the water at the surface continue to dry, but no sudden changes. So gradually it drops in terms of water content. Second, the profile front continue to move downward with a sharp boundary between wet and dry soil region. So as the water at the surface continue to dry, the waterfront, here is the waterfront, continue to move downward and downward. So there is a sharp surface appearing. So here initially is t equals to 0. When t equals to 1, so the water content at the surface drop, but the waterfronts continue to move downward. So at t42, so the waterfronts move even lower and lower into the soil. So this is the first cycle. So we can also do it for the second cycle and third cycle. So you will still see the same observation, same kind of trend, but just that the water will go deeper and deeper into the soil. Okay, this slide shows a simplistic view of what we have just talked about in the previous slide. So initially you have this amount of water, all right, but as the time continues to increase, you stop the water. So if you stop the water from coming in at the top, as the time continue, so the water, the same amount of volume will still move down into the soil, but it will be redistributed from this shape into this dashed line shape. Okay, so figure 4.22 is referring to the rectangular approximation to the redistribution process, okay, of water infiltrating into the soil.